All right, today we're going to be talking about section 12.5, the last section in chapter 12. We're going to be talking about normal distributions. We're going to be talking about discrete and continuous random variables. We're going to be talking about what is a normal curve and what are the properties of a normal curve. We're going to talk about a table that has standard normal curve areas in it and how to interpret that table. So the first thing we're going to look at is what they refer to as discrete random variables and continuous random variables. And the best way to think of a discrete random variable is that a discrete random variable is countable. So what we mean by countable is that, for example, if I wanted to count how many times I rolled or how many times I got ahead when I flipped a coin, or the number of people that attended something, then we're talking about a countable number. Whereas a continuous random variable is something that's not really countable. For example, if I'm measuring something like how wide a flower is, or how many inches something is, that could be a number that is 1.2, 1.25, 1.27. So it's not really a discrete number. So that's the difference in what we're referring to as the discrete random variable or a continuous random variable. So one of the big topics for this section is the normal curve or the standard curve or the normal distribution. And when we're talking about the normal curve, one of the things they talk about here is the standard normal curve. And it refers to the fact that we're looking at the number of standard deviations from the mean. And this is just simply the z-score. So remember in the last section we talked about finding the z-score. So the standard normal curves that we're going to be talking about in this section do use the value of the z-score. So a normal curve is just basically that bell-shaped curve where we want everything to be evenly distributed around this curve. The average is the middle of the curve, and then we should have a set number of deviations to each side. So these are examples of some different normal curves that you can see. S is what we refer to as a standard normal curve, the red line that you see here. And you'll notice that here we have 0, which represents the mean. And if you look at the first example for S, you'll notice that here we have 0, and it's right in the middle of the curve. And the standard deviation is 1, so it's evenly distributed on either side. Whereas A, the standard deviation, the mean, is over here less than 1. And again, the standard deviation is fairly spread out, so we have a nice standard deviation of 1. B has the same mean as S. So again, here's our mean coming right up here through the middle for B. But you'll notice that the data is less spread out. The standard deviation is less than 1. It's got a smaller deviation from the mean. And C, the mean is greater than 0, so it's over here skewed to the right. And the standard deviation is greater than 1, so again, it is more spread out. This data is more spread out. All of these are considered to be normal curves, but the difference is where is that mean. So here are the big things about the properties of normal curves. The first thing, normal curves are bell-shaped, and they're symmetric about that vertical line through the center. The mean, median, and mode of a normal curve are all equal, and they are at the center of the distribution. So that's probably the most important thing about a normal bell curve. The empirical rule, this is very important. These numbers are very important. 68% of all of the data values in a normal curve lie within one standard deviation of the mean in both directions. 95% of the data lies within two standard deviations, and 99.7% of all the data lies within three standard deviations. So the likelihood that you have data beyond three deviations from the mean is extremely rare. In those cases, you might call that data an outlier, or they might be an extreme to the situation. So here we have, here's our average right here in the middle. So 68% of the data that's collected is going to fall within this first standard deviation from the mean. 95% is going to fall within this data range, and 99.7% is falling within this data range. So if we take that 0.3% that's left over there, that means that we have, in this data range, you're going to have 1.5, and in this, or 0.15, and in this data range, you're going to have 0.15. So it's extremely unlikely that you will have any data in this fourth standard deviation. So let's say we had 280 sociology students that took an exam, and the distribution of their scores should be treated as normal. How many scores should fall within two standard deviations of the mean? So we already talked about that 95% of the data should fall within two standard deviations of the mean. So if I take the 280 sociology students and multiply by 95%, which is 0.95, I should be able to tell how many of these students should fall within that two standard deviation mean. And so the number of students that should fall within that mean are 266 students. So what if I said how many of the students should fall within one standard deviation of the mean? So if I wanted to know one standard deviation from the mean, then I would take the 280 students and multiply by 0.68. And so I should find out that 190.4 students should fall within that one standard deviation of the mean. Now for this next part, there's a table in your book on page 671, and I'm going to minimize this and show you that table. And that table looks like this. And what this table is a little bit different than some of them you'll see, and I do have a copy of this table posted out on Blackboard, and I do expect that you will have a copy of this table in your notes so that when you take your test you'll have a copy of this table. So what I want you to notice here is that this table is based on z-scores. So 0 is the middle of the table. 50% of our data is going to fall to the right of that mean, and 50% of our data is going to fall to the left of the mean. So if you'll notice here, remember we've said that you're not going to have any values beyond that third standard deviation. So you'll notice here that when the z-score is 3, you'll notice that the area of the under the curve is 0.50 because it's 50%. So again, this table doesn't go beyond 3 because you can't have a standard deviation greater than 3. It's not rarely ever going to happen. So what we're finding here, and this is a good one to look at here, is that when you look at, for example, the 1, remember we said that one standard deviation from the mean is 68%. So you'll notice that what you have here is 0.34, because what they're giving you in this table is, it's my mouse, so it'll be a little easier. What they're giving you in the table is the value to the right or the left. So they're telling you that 34% of the data is falling to the right of 0 or to the left of 0, one standard deviation from the mean, or one z-score. So that's what this table is giving you. So just keep that in mind as you're working through these problems. So let's go back to this. And so this table, again, gives you the fraction of all the scores in the normal distribution that lie between the mean and the z standard deviations from the mean. So it tells you, you can figure out the above and below values using that table. So what if I wanted 1.5 standard deviations above the mean? So if I look at that table and I find 1.5, you'll notice that the number in the A column is 0.433. So that would be 43.3% of my data lies 1.5 standard deviations above the mean. If it said below the mean, it would be the same answer. Okay? If it said above and below the mean, then I would double that value. 2.62 standard deviations below the mean. Again, we're going to look up 2.62 in the chart, and we get 0.496, which is 49.6%. Okay, so again, one of the things you've got to keep in mind as you're looking at this is that from the mean to the far right is 50%. So 1.5 standard deviations is close to all of our data to the right. It's 43.3% of the data, which is accurate. Okay, and there's our example with the 2.62. So what if I had this example and I wanted to find the total area indicated by the region? So I actually have two values I have to calculate here. I have to look at the 1.7 z-score, and if I look at my chart under 1.7, I'm going to get 0.455. And if I look in my chart for a z-score of 2.55, I end up with a value of 0.495. And so to find the area of all of this shaded region, I want to add those two values together, and I get 0.950 as the area under the curve, which is 95%. Okay, so what if I wanted to do something like this? Again, I wanted to figure out what's the area of the curve. If I can figure out the area of 0.61, which would be this part right here, and I figured out the area of 2.63, if I subtract those, I'll figure out what's left over. So 0.61, the z-score, has an area of 0.229, and 2.63 has an area of 0.496. So again, I want to figure out what do they have left over, or what's the difference between the two. So if I subtract that, I get 0.267. So that would be 26.7%. Okay, so if I wanted to find the area of the region in the color below, now remember that when you're finding the values in the chart, you're finding out the percentage from the area, from the mean over to the right. So you're finding out this. If I want to know this part, I have to remember that the entire right side is 50%, or 0.50. So if I figure out what part I have right here, and I'll call it green, if I figure out the part in green, then if I subtract it from 0.50, I'll know the part that's shaded here. So looking at our chart, we're going to look up the 2.14, and we find out this area here is 0.484. So again, if I want to know the shaded area, I'm going to say 0.50 minus 0.484, and we're going to end up with an area of 0.016. Okay, so when we're looking at standard normal curves, we can think of these as percentages, or the probability that it's happening, or the area. And the standard normal curve is giving us all of this information. So let's look at an example that involves that chart. That's a realistic problem. So we're talking about the volume of sodas in bottles from a small company. So you know that when you've got these companies that are bottling something or packaging something, that even though it says 3 ounces on the package, it's not always exactly 3 ounces. So most of these companies have an acceptable deviation from that 3 ounces that they have listed. So here we have a soda company, and the soda company promises that they have a normal distribution, that their average or their mean is 12 ounces, and the standard deviation is 0.15 ounces. So they say if they randomly pick up a bottle, what's the probability that it's going to have more than 12.3 ounces? So the first thing we need to do is find the z-score. So the z-score, remember, we calculate that by taking the number that we have, 12.33, subtract the average, and divide by the standard deviation. So our z-score in this case comes out to be, sorry, I had to find my notes, 2.2. Okay, so now we want to know what's the probability that it will have more than 12.3 ounces. So our z-score is 2.2, and we're wanting to know what's the probability that the area is over here. Remember, this is 0 because this is our average. So we're wanting to find this value here. So remember, we have to do the 0.50 minus the value that we get from the chart. So when we look in the chart for 2.2, we're going to find a value of 0.486. And then again, we're going to subtract that from 0.50 to figure out the probability that it's going to be greater than 12.33 ounces is 1.4%. So it's a very small probability that that's going to happen. So here's another example like that. A machine that fills milk cartons is set up to average 32.2 ounces per carton with a standard deviation of 1.2. What's the probability that it fills a carton less than 32 ounces of milk? So again, you got to think about your standard. Standard curve as you're thinking about this. Oops, I'll try and draw a good one. I didn't draw a very good one. Here's 32.2. So 32 is over on the left somewhere, so we want less than 32 ounces. So let's do our z-score. 32 minus 32.2 divided by 1.2 comes out to be and I forgot put my notes away. Let me grab my answer here. It turns out with a z-score of negative 0.167 or negative 0.17. I didn't put the negative down here because it really didn't matter when we looked in the chart. So then we look at the probability in that, and we'll find out that the probability of that is 0.067. And we want, remember, here is that 32 right here. We want to know if it's less than that. So again, we have to subtract it from 0.50. which says it's 43.3% likely that it's going to contain less than 32 ounces of milk. So that's a pretty good possibility that we're not going to have exactly 32, or we're going to have less than 32 ounces of milk. Okay, so here's another example. Assuming a normal distribution, find the z-value meeting the condition that 39% of the area is to the right of z. So this time we're going to do it a little bit differently. Instead of, we're going to show you here. So because 50% of the data, or the area to the right of the mean, there has to be 11% that is here. So we're looking for 39% of the areas to the right of the z-score. Here's the z-score we're trying to find. So again, I know 11% has to be in here if 39% is over here. So what you're going to do is you're going to go to your chart and you're going to look for, go to my chart real quick. Sorry, I accidentally closed it. And when we look at our chart, what we're going to do in this chart this time is we're going to look in the A column, and we're looking for 0.11 in the A column. And you'll notice that we find 0.11 right here. And the z-score is 0.28 for that value. So when we go back to our problem that we were looking at and we look at the z-score, it corresponds to 0.28. All right, let's look at one last example. So assuming a normal distribution, find the z-value meeting the condition that 76% of the area is to the left of z. So again, when we think about that, we already know that 50% is over here. So we're looking for that 26, we're looking for the z-score. We're looking for a z-score that gives us 26% in this area right in here. So again, when we look at that table and we look for 0.26 in the A value, we end up with a z-score of 0.71. All right, so I hope this helps. We're going to be getting ready for a test soon. So keep your eye on the material. If you're having any problems, let me know so that we can get those resolved before your test. I hope you have a great week, and also our notes, don't worry about it. Have a great week.